here's my magic trick. I have a deck of cards, regular ordinary deck of cards. I'll show you guys in a minute. You can see they're all totally ordinary cards. And I'll go ahead and give them a quick shuffle. Alright, so I'm going to memorize the first 26 cards of this deck. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Okay, good. Now I'm going to lay out 3 cards. Let's see that again. 2, and 3. And then I'm going to complete down to the rest of it. So this is to 10. So this is 6. I need to go 7, 8, 9, 10. 7, 8, 9, 10, and 8, 9, 10. And I put the cards I memorized are on the bottom. Now I'm going to add these up. 6 plus 7 is 13, plus 8 is 21. So the 21st card in this deck is going to be the King of Diamonds. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21.
Oh my gosh.
So that is completely mathematical. It has nothing to do with magic. I actually learned it from this guy in a pub in London did it for me and my friend when we flew in and we went in there for a drink. And it took me a few times to watch it before I kind of figured it out, and it took me a couple times trying it before I got it right. But what was that?
I didn't know.
But you guys can all figure it out. Just it's all mathematical, no magic at all.
Did you shuffle?
You can I shuffled in the beginning, but then I memorized the first 26 cards.
As you were going?
Yeah, I showed you guys. I showed, right?
Yeah.
And then I turned those over. I put those on the bottom, and then
Did you memorize 26 cards like that?
I don't think so. No, I didn't.
What happened?
I did not.
So you're not getting colors?
No, you have to figure it out.
Can you do it again? I wasn't paying attention.
I'll do it in next class.
Oh, the 10.
Okay. All right. So let's get back to our what we've got here. So left problem number 5. So you guys do something that looks like this, right? The top, what is it? Top 20%? So you guys did this and you put 20% goes over here. So then you need to find the left area, because you want to find this z-score here. So you found the left area, and this area over here is what? 80%, so 0.80. And then you did inverse norm of the left area, 0.80 or 0.8, and you got what? 8416? 84. Okay. So then 0.84. And then you need to convert that to a z-score. You can't just say to your friend, hey, you have to have a z-score of 0.84 to get into the police academy. He's not going to know what that means, right? You have to tell him you need to get a score of blank on the test. So our x value is our mean plus our z-score times the standard deviation, right? So the average is 200, but then he needs to be 0.64 standard deviations above that. Oh, sorry, 0.84. 0.84 standard deviation. The standard deviation is 20. So 0.84 20s above that. 200 plus 16.8. So he needs to have 216.8 or higher to get into the police academy. Okay. Good. Do you guys need a second to check into neighbors, or everybody kind of okay with this?
No, John.
I'm sorry? Good? Okay. Great. Now we're going to talk about the central limit theorem. Kind of a big thing. Brandon, you haven't read today yet. Go ahead.
In addition to knowing how individual data values vary about the mean for the population, statisticians are interested in knowing how the means of samples of the same size taken from the same population
Exactly. So that's what we're going to be looking at next. How means of samples vary around population mean. So first of all, I'm going to talk about the fact that there are many different kinds of distributions. Some are discrete, some are continuous. We've talked about two so far, binomial and normal. There are many others. One that we have is, so binomial, well first let's look at binomial for a second. Binomial, what's the thing that varies? What's my variable in binomial? What's the thing that changes within a problem for binomial? What's my variable? Anybody? X? X. X is my variable. What does X represent? Number of successes. How many successes I have, right? Probably X is 2, probably X is 1, probably X is 0. Do you guys remember that? 0 successes, 1 success, 2 successes. So, number of successes, is that discrete or is that continuous? Discrete. Because I can't have 1.34 successes, right? I can only have a certain fixed number. So binomial is a discrete distribution. Normal is continuous. Because normal is this curve, and it can be any two numbers inside of there, and you find the area between them. So normal distributions are continuous. Binomial are discrete. Those are the first two that we know about. We're going to learn one more today. But let me first mention a couple other ones so you can get a flavor of the idea of what different distributions could be. So one distribution is binomial. I know ahead of time how many times I'm going to flip the coin, right? I know before I start, I'm only going to flip it 10 times. This one here, I don't know when I'm going to stop. I'm going to keep flipping until I get 8 successes. So my number of successes is fixed, and my n is sort of my variable. Does that make sense? I keep flipping until I might flip 8 times and get 8 heads. Or it might take me 100 flips before I get 8 heads. I'm just going to keep flipping until I get 8 heads. So that's one. Another one is how much time between events happening. So, for example, I want to know how much time between white cars driving by on the freeway. So it'd be white car, 1 alligator, 2 alligator, goes down 2.4 seconds. 1 alligator, 2 alligator, 3 alligator, 3.6 seconds. Right, so time between events happening. Actually, it was really interesting in my grad school. My professor was talking about how when they were learning through stuff, I guess he went to Stanford, but there was this one area on campus that bikes would always wipe out. Like there'd always be like someone who always just totally wipe out. And so they kind of did. They counted the number of days between like major wipeouts where someone got injured when they wiped around here, and it'd be 2.7 days or 1.6 days. So it'd be how many? So kind of they come with this average time between people wiping out around this curve. All right, so that's another one. But the one we're going to talk about today, and we're going to learn about, is you waiting for a bus that comes every 20 minutes. It's a magic bus. You don't know when it starts in the day, but once it comes the first time in the day, every 20 minutes exactly, it comes again. 20 minutes again. So every 20 minutes it comes. Good? Is that everybody with me on this one, understanding it? Okay. This is what we call a uniform distribution, because all these values are equally likely. I'm just as likely to get here, get lucky, and come, and right away the bus comes. And I wait 0 seconds, 0 minutes. Or I could be unlucky. I get there right after it leaves, and I have to wait all the way until 20 minutes, right, before it, or just fractionally before 20 minutes before it comes. So any one of these possibilities is equally likely. I could wait anywhere from 0 to 20 minutes. What is my expected wait time? Take 15 seconds with your neighbors and see if you can figure out what is my expected wait time. Go ahead. On average, how long will I wait? What's the lowest amount of time I can wait? What's the most amount of time I can wait? It better be somewhere in between there, right? What's my average time? 10, right, because for every time that I end up getting really lucky and waiting here, I'm going to get unlucky and wait this much, right? For every time that I'm sort of medium lucky, I might be kind of medium lucky that way. Or for every time that I'm kind of like almost the average there, I'll be almost the average there. Does that kind of make sense? They kind of balance each other out. Okay. So this is what it looks like. This is what so we know that the area underneath every curve equals what, guys? Area under a probability distribution curve always equals 1 or 100%. This curve is shaped like this. Why? Because less than 0 minutes, I'm never going to wait less than 0 minutes. And it's a magic bus. It comes every 20 minutes, so I'm never going to wait more than 20 minutes. So this is impossible, this is impossible, but everything in between, from 0 to 20, is all equally likely. So it goes 0 probability to equally likely probability, back to 0 probability. It makes a rectangle, uniform distribution. What's the probability I wait 0 to 1 minutes? What do you guys think? From 0 to 1 minutes. 1 out of 20? 1 minute out of 20 minutes? That kind of makes sense, right? So 1 out of 20. And this we can back up because we talked about the fact that area is the same as probability. They're the same thing, right? Area under the curve is the same thing as the probability. So what's the area of a rectangle? Length times width. In this case, it's going to be length times height. So from 0 to 1, let's back it up a little bit. We know this whole rectangle is equal to 1, right? The area of the whole rectangle. What's my length? How long is this rectangle? 20. So if length times height equals 1, equals my area, here I'll show you what I'm talking about. My area equals length times height. Good? My area is 1. My length is 20 times my height. What's my height have to be? Divide both sides by 20. Height has to be 1 over 20. In other words, the height, because the area is 1, then for the distribution, the height of this rectangle is always going to be the inverse, the reciprocal of the length, 1 over the length. If the length is 12, what's the height? 1 over 12. If the length is 8, what's the height? 1 over 8. Good? All right, so here, my height is going to be 1 over 20. That's how tall this is. So if I look at from 0 to 1, and I look at this area here, we said the height is 1 over 20. What's the length? How long is this little rectangle here? 1. So this particular area is going to be 1 times 1 over 20. 1 over 20. Make sense? Good. Now you guys figure out what's the probability that I wait between 5 and 10 minutes. So here's 5 minutes, 10 minutes. What's the probability that I wait between 5 and 10 minutes? Take 20 seconds with the neighbors and find this. Okay, so what's my height again, guys? 1 over 20.
Keep beating your heart.
Doesn't change, it's the whole rectangle. So, and then what's my length? 5. So the area should be 5 times 1 over 20, right? The height doesn't change. Once you fix it for the problem, it's set. This height's always going to be 1 over 20. Right? I'm just going to find areas of small sections of it. So this is going to be 5 times 1 over 20, 5/20ths, or 1/4, or 0.25. Yes?
So we always go with the least that's smaller than minimum, so like 5, not 10. Or no, the length.
No, it's a length. How
Okay.
far is it from 5 to 10?
5.
Right,
Okay,
yeah.
that makes sense.
Good. Thanks for asking that. Right, so the length is how far is it from 5 to 10? 5. Here it is prettier. And again, the area under the rectangle must equal what? 1. Good. How do you find the height? How do you find the height? What was that? The height. How tall is this rectangle? It's always 1? 1 over 20, which is 1 over the what? For any rectangle, 1 over the length. Or you're going to say area divided by the length? Yeah, that works too. All right, good. So you guys need to do this problem at the bottom. So remember, the length of this, find the length of this. Doesn't necessarily have to start at 0.